Okay, so after my lecture 1, now in this lecture we will learn about some thermodynamics of ideal gas. Okay, so let us start from the very known formula of canonical ensemble. So our today's topic of discussion is thermodynamics of ideal gas. So for that we will start with a canonical ensemble theory, where the probability that a member of an ensemble is in the state having energy ER is given by e to the power minus beta ER divided by this, where beta is 1 by kT. And from that we have already defined in our previous class something called partition function of a system, which is given by this. So I have already told you that the thing called partition function is extremely important for studying any thermodynamic property of any system. Just যদি তোমাকে বলা হয় মানে যে কোনো কিছু থার্মোডাইনামিক প্রপার্টি যদি স্টাডি করতে হয়, তাহলে প্রথমেই ক্লোজ ইউর আইজ এবং চোখ বন্ধ করে প্রথমেই তোমাকে যেটা বের করতে হবে সেটা হচ্ছে পার্টিশন ফাংশন অফ দ্যাট সিস্টেম। এবং ওয়ান্স ইউ নো দ্য পার্টিশন ফাংশন অফ আ সিস্টেম, ইউ হ্যাভ all the cards in your hand and you can find out almost anything using this function. Anything includes the internal energy U of a system. What is the internal energy U of a system in the language of statistical mechanics? It is nothing but the average energy of the system, which is given by sum over PR ER, and after a little manipulation it can be shown that E bar in terms of partition function is as simple as this. So E bar in the language of statistical mechanics and U in the language of thermodynamics. So this E bar is nothing but the internal energy U of the system. Okay. Now next we are going to discuss something a little bit different and very important from the point of view of thermodynamics. So we all know from the first law of thermodynamics, dq is equal to du plus dw, work done, internal energy, heat supplied. Now if a system is having average energy E bar, then we have already seen that E bar is nothing but U, and the work done by a system when no heat is supplied. যদি আমরা বাইরে থেকে আলাদা করে কোনো এজেন্ট সাপ্লাই না করি তাহলে তার মানে this means dq equal to 0. যদি আমরা বাইরে থেকে কোনো হিট সাপ্লাই না করি তাহলে the work done by a system dw is obviously minus du or minus de bar. Clear? Now if we define one particular parameter x and we define the generalized force corresponding to this particular external parameter small x. So small x is our external parameter and capital X is something called generalized force which is related to this external parameter. So if small x is our generalized displacement and capital X is our generalized force, then dw can be written as x bar dx. This is average of the generalized force. Average over what? Average over all possible energy states of the system. Clear? So now we have two different things. One is dw equal to x bar dx. So this is our definition of generalized force, and the other thing which we have is this d bar w is equal to minus de bar. Now this can be written as del er del x dx, because I have already told you that the average means the average over different possible energy states and here dE, in place of dE we are writing del x of er times dx. Clear? So we are writing the energy differential considering the fact that যদি external parameter x চেঞ্জ হয় তাহলে এনার্জি স্টেটটা চেঞ্জ হবে. If x is changing, the particular energy state will also change. Hence any differential in ER can be written like this, and this is the average. Clear? So by comparing this and this, we now have the bridge, the relation between the generalized force in thermodynamics and the microscopic quantity from statistical mechanics, and the relation is eta. So x bar is given by minus del del x er bar. ওকে, নাও এবার আমাদের নেক্সট টার্গেটটা কি? আগেই বলেছে যে আমাদের নেক্সট টার্গেট হচ্ছে যে বিশ্ব সংসারে যত রকমের থার্মোডাইনামিক্স আছে সেটাকে কোনো একটা ভাবে পার্টিশন ফাংশনে নিয়ে যাওয়া। সো হোয়াট উই ওয়ান্ট ইজ অল থার্মোডাইনামিক্স to be expressed by the partition function. So let us try. তাহলে আমরা কি পেলাম? x bar is minus del del x year average. এইটাই আমরা এখন ক্যালকুলেট করব। ওকে, সো দিস ইজ মাই PR e to the power minus beta ER divided by sum over e to the power minus beta ER, and my quantity is del del x of ER. Therefore, the average of this obviously will be A. Okay, now plugging in the expression for PR, A. Clear? This is our standard method for determining any particular statistical average. বেশ, এইবার now we will work with the above one. So to the power minus beta ER del ER del x, this can be written as minus 1 by beta del del x. আগেই বলেছি যে our target is to express x bar in terms of the partition function of the system. সুতরাং যাই আমার ক্যালকুলেশন থাক, যাই থাক না কেন, আলটিমেটলি I have to bring out this thing. এই জিনিসটাকে আমাকে নিয়ে আসতেই হবে, তো সেটাই আমি এখানে করলাম। we have written this quantity like this, এবং ডেরিভেটিভ করলে দেখা যাবে যে এই জিনিসটা we are getting it back. So it is minus 1 by beta del z del x. Okay, so now what we are getting is evident. So what we are getting is for this. I am writing it on the reverse. So it is minus 1 by beta del z del x divided by z. Clear? So it is, and this minus sign, and here there is another minus sign, so it will be plus. So finally this is 1 by beta del x of log z. So the take home message is, our generalized force, again a thermodynamic quantity which is macroscopic, and partition function which is statistical mechanical quantity and microscopic, and they are related like this. This is our thermodynamic quantity, macroscopic, and this is the partition function is stat-mech quantity which is microscopic. Clear? And establishing the bridge between the two is the goal of studying stat-mech, or why you are studying stat-mech at all. বেশ, তাহলে এবার if we apply this, if we take as our example, suppose our external parameter is volume. তাহলে in that case, so our generalized force obviously is pressure. Pressure is something which changes the volume of a system. সুতরাং dW is P bar dV. We are familiar with this thermodynamic quantity, and P bar can it be calculated from the partition function? Yes, of course. The P bar will be 1 by beta del V of log z. In my next lecture, we will use this formula for ideal gas. There we will find out the partition function for an ideal gas, and we will show the celebrated ideal gas equation PV equal to nRT. But sorry, okay. But before that, I would like to go into some more details of thermodynamics, like for example entropy. Entropy in terms of partition function z, and free energy which is U minus Ts, or in our statistical language E bar minus Ts, in terms of partition function z. Okay. Since we already know that there are two important parameters with respect to the variation of log z. What are those parameters? One is the external parameter x, and the other is the beta, or the temperature T. these two things are able to affect the energy states of the system, and therefore they are able to affect the partition function of the system. Sutorang d log z is del del x clear? Now we know we have derived this, and also we have derived clear? So we can write equation 1 like this, এবং x bar dx is nothing but beta dw, and this is minus e bar d beta, and with this we will write beta de bar minus beta de bar. Now taking this and this together, hope there is no confusion. We have taken this and this together, clubbed together, and written it like this. So ডান দিক থেকে বাঁ দিকে নিয়ে এলাম, তাতে আমরা পেলাম এইটা, and obviously what is this? This is this. Okay, now we will divide both sides by t. And we know that dq by t is ds. So a little bit of simplification will show you that S is k E bar. Just put ds in place of dq by t and write beta equal to 1 by kt here, and the t's will cancel out. Take the k on the left hand side, and then you will get the entropy in terms of the partition function. And our next target was to find out the free energy, E bar minus ds. Here we will use this formula for entropy, and upon simplification we will get that free energy is as simple as this. So now you know how powerful the partition function can be. In our next lecture, that is Statistical Mechanics Part 3, we will study that actually how powerful this partition function can be with our example of ideal monatomic gas. Okay, thank you so much, students. Have a nice day.